So let's look at evaluating logarithms. So as a reminder with the form, we're going to be given the logarithm, we'll be given the base that we're working with, and then we'll know the input for the logarithm, which is the value y. And then what we're solving for is an exponent. So another way to think of this is when we're solving our logarithms is we know the base, we know the value that comes out of it. What we don't know is the exponent, and that's what we want to solve for when solving our logarithms. So in evaluating the logarithms, we'll always end up with equals and then some number or expression that should be coming from the exponent that's needed. So let's talk about doing these without our calculator. So I'm going to put the equal sign, and we're going to be putting a number there. But like I said, off to the side, what I like to think about is we have our base, we don't know the exponent, and we know the outcome is 8. So what I want to know is what exponent is needed on 2 in order to get 8 out. And what I know is that I would need a 3 right there. 3 is the number that I would need in order to get 8 out. So with that, my solution to the logarithm, that would equal 3. Here, it's the equivalent of 5 to what exponent would give me 25. So again, I'm taking the base, I don't know the exponent, but I know the outcome. I know what the value should be. And what I would need is an exponent of 2 to get 25 out. So with that, this logarithm would equal 2. So just keep in mind this is side work. It doesn't really connect directly with the logarithm. So I'm doing this off to the side just because I'm typically more comfortable with our exponential form. So if it helps to think of it in exponential form to get the answer out, that's fine. But with logarithms like this that we're evaluating without a calculator, there isn't really any work to be shown. It's just how we think about it. That's what I'm trying to show you with this, is how we're thinking about it, so how you can think of that answer. But in the end, all we do is say that logarithm's equal to that number. A logarithm of 100. So what I'm thinking about off to the side here is 10 to what exponent would give us 100, and we would need an exponent of 2. So with that, this would be a 2. Now I want to show you a trick with these logarithms that are base 10. Like let's say this is 100,000. There's this nice trick where if it's base 10, you can just count the number of zeros that are showing up. Like up here, where we have this log base 10 and 100, we have these 2 zeros. It's coming from this exponent rule that we'll talk about when we look at logarithm properties, but as a nice little shortcut, is if I have log base 10 of 1 followed by a bunch of zeros, all you need to do is count the number of zeros. So 1, 2, 3, 4, 5 zeros. So that would be 5. So that's a little shortcut with those. Alright, log base 3 of 3 to the negative 2. So we could go through and simplify this. However, this is actually better in this form because what we're trying to do is, so if I take my base, so base of 3, and I don't know the exponent, but what it should equal to is the value that's inside the logarithm, which is 3 to the negative 2 power. So let's think about what this is saying. It's saying 3 to what exponent gives us 3 to the negative 2? Well, I need that negative 2 where that question mark is. So this is actually equal to negative 2. And this is going to be a logarithm property that we talk about when we get to those videos, but it's just something that naturally comes up here. But we'll revisit this even more. But the property goes, if the base of your logarithm is the same as the base of an exponent for the value, it's kind of like they cancel out with each other because they're showing you the exponent that's the answer. If our question is what's the exponent, and they're showing us the exponent right there, then that's just going to be your solution. So we'll look at a few more of those. All right, with questions like this, where I'm wondering 2 to what power gives us 1/4. So when we start with a base that is a whole number like that, and I see that I'm getting a fraction out, I want you to think negative number. In order to have this change like that, we need a negative number in that exponent there. So let's just say I put 2 to the negative 1. That would be a 1/2. So then what I could think is, okay, what exponent do I need on 2 in order to get a 4 out? And I would need an exponent of 2. So what this can help me see is that in order to get from 2 to whatever exponent to a 1/4, I'll need a negative number, and it should come through as that 2. So what I would have is 2 to the negative 2 power is equal to 1/4. But as I was mentioning in the last video, if you recognize it's a fraction, then just keep negative in the back of your mind, and it comes down to those two numbers right there, the 2 and then what's showing up in the denominator. And just knowing that 2 squared is equal to 4, well, that would give you the 2 portion, and then just seeing that you're getting a fraction out means it has to be negative. So this logarithm is equal to -2. All right, log base 4 of 1. So I want to know 4 to what power is equal to 1. And the exponent we would need right there is a 0. 4 to the 0 power is equal to 1. So with this, we'll have an outcome of 0. And this is connecting to the idea that anything raised to a power of 0 is 1. So let's say I change this a little bit and said take the logarithm base 135 of 1. Well, if I'm thinking 135 to what exponent is equal to 1, that's just 0. Even though I have this super complicated big base there, if I'm getting 1 out, then it has to be an exponent of 0. So these two values are going to tie together. And we'll talk about this again as well with the logarithm properties, but this is going to be an identity property. So we'll have this connection between value of 1 and exponent of 0. All right, some more here. So this is log base e, and this ties closely to what we just talked about up here. But if it helps, you can imagine that there's a base e there. So what I'm doing is I'm taking base e, and I want to know what exponent do I need to get e cubed. Well, those should be the same number for that equation to balance. So I need an exponent of 3. So this is the same case as up above there, where the logarithm has the same base as the base of the exponent and the value. So if we want to know what exponent do we need on the base to get this, well, they're just showing us the exponent right there. So it's kind of like all of that cancels out, and we're just left with the exponent. Here, what we can do is a few things. We could just think e, so base e to what power would give us 1 over e. And with that, we see we move to the denominator. There isn't an extra exponent on, there isn't an extra exponent on it, meaning there isn't a number showing up there. So with that, all we would need is an exponent of -1 to move it to the denominator, and that would give us 1 over e. So the exponent we would need is a -1. If it helps, you could also change it in this form. What we could have done is written this as natural log of, and we know 1 over e is the same thing as e to the -1. And then you could think about that cancellation that we just talked of base e with the base of the exponent there. So all we would be left with is that exponent of -1, same thing. So whichever method you like better will get you to that same answer. All right, and this one here, so 6 to what power? So we have base 6 to what power would give us the square root of 6. And this is where we need our rational exponents. So the equivalent of the square root is an exponent of 1/2. Again, that denominator sets the level of root that you're taking. In this case, it's a square root. It has to be in the denominator there. So this is going to be a 1/2. So if you start seeing radicals showing up in this value portion here, you're going to be getting a fraction out over here, because you would need a rational fraction in order to evaluate that. Again, you could change it in this original form, so logarithm base 6 of, and just writing square root of 6 as 6 to the 1/2 power. And then you could think about that cancellation of those bases there, and that all kind of wipes out, and you're just left with your exponent of 1/2. All right, so there's some examples of evaluating the logarithms. Again, in the participation, we'll get a lot of practice with those. Solving some equations, and in our following week, we're going to look at more complicated equations to solve. But with these ones, we can kind of get by with what we have so far. So what we have here is something that's in exponential form. And the key is I want to solve for x, and x is trapped in the exponent. So because I want to solve for the exponent, that's the whole idea behind logarithms. So if you're ever solving, and especially when we get to later in the course, final exam where we have all of these different types of equations that we can solve, if you ever think like, oh, my variable is stuck in the exponent, that's what logarithms are used for. So try to make that connection of solving for an exponent is what logarithms are all about. So in order to solve for x here, what I need to do is, it's like I want to untrap the exponent. So what I'm going to do is move things around. So I have base, so a base of e. I have my exponent of -2x plus 1, and this overall value of 13. So I'm going to drop down the exponent to be on one side of the equation, so -2x plus 1. A logarithm base e, which is the natural log, of our value of 13. And then we can start solving. So we can start solving for x as we usually would. Now, this logarithm of 13, it's like that function notation. What I want you to do is think of this like a block. We can't break into it. We can't break out of it. It's just kind of stuck. It's kind of like, think of it as if we had like the square root of 13. We would have to have some special things in order to subtract 1. Like the -1 would go on the outside. It doesn't subtract from in there. Same thing here. The -1 is going to go on the outside. Or like dividing by 2, that happens on the outside of our radical function. Same thing's going to happen here. So that 13 is trapped inside of this logarithm function. So we're not going to be able to do these operations onto that number itself, but the operations can happen around it. So if I subtract 1 from both sides, what that would look like is -2x. equals, and then I'll have that whole natural log of 13 minus 1. Now I'm writing the parentheses in there. You could write this as just natural log of 13. However, I find that without the parentheses, instinct kicks in. It's like, ooh, I want to do that 13 minus 1, which is 12. But we can't because it's attached to the logarithm. And there's something about having the parentheses that gets our mind to think more, okay, those are connected. That minus 1 can't change that 13 there. All right, my next step would be to divide by -2, divide by -2, which is x equals, and then in this exact form, I would write it as natural log of 13 minus 1 over -2. So this would be my exact answer, which is often what we want to find first. If we needed a rounded answer, we can go to our calculator. So let me show you how to type this in. So I'm going to set up my fraction, do ln of 13 minus 1 over -2, which is a negative 0.7825. So with that, we can get a rounded answer, or an estimate. Okay, let's look at another example. So with this one, the variable that we're solving for is trapped inside a logarithm. So to get out of a logarithm, we need the exponential form. So when we get to solving equations and we have these exponential forms and logarithm forms, we're often going to find this exchange of moving between the different forms. So with this one, we have the base. 5x minus 4 is the value, so that's going to be alone on one side of the equation. And then we have our exponent. And again, it can be helpful to make this little note when you have this logarithm of stuff equals something, that thing on the other side of the equation is representing an exponent. So I'm going to take that base of 3 and exponent of 2, and then equals everything in the parentheses there, everything inside the logarithm. So 5x minus 4. So this is a 9 equals 5x minus 4. Add 4 to both sides. Divide by 5. Nope, I subtracted there. I went too fast. Divide by 5. So x is equal to 13/5. Now, as we talked about at the end of the last video, we're going to have limitations in terms of what can go inside a logarithm. Talked about how negative numbers don't work. So when we solve here, we have to check that it works. So checking here, so I have log base 3 of 5 times 13/5 minus 4, which is going to be the same thing as log base 3 of 13 minus 4, which log base 3 of 13 minus 4 is 9. So solving this logarithm, I'm thinking 3 to what exponent gives us 9? Well, that would be a 2. And that is exactly what we wanted for our exponent there. So that all checks out. Alright, so there's a little bit of solving equations, but also evaluation of our logarithms.